Hi class, this is Juan Ramirez with EE 2715. This is the first out of a three sort of video series with different examples on first order circuit analysis. So we covered first order circuits in chapter 7 of the book and looked at what the RC and RL circuit response is when it's initially charged and gets discharged, and also what the response looks like when you apply a step function as the input. So let's start off with an example, and for this example, you could just simply follow along. So we're going to look for the output voltage. All right, so here's the circuit we're analyzing. I'm just going to kind of fill in some remaining values. Okay, so initially means before time 0, the switch is closed, and that 8-volt source with the 2 kilo ohm resistor, they are part of the circuit. As soon as time hits 0, the switch opens instantaneously, and afterwards, switch being open, the 8-volt source is no longer in the circuit. And this creates a transient response for the capacitor voltage, and this also changes what the output voltage looks like, Vout. All right, so let's go through our step-by-step process. If you recall, there's 6 different steps that we take. So step 1 is to find the initial voltage. So we call that the initial state. That's for time before 0, assuming it was in steady state. So assuming the switch was in that initial position for a long time. And so what we do is we replace the capacitor with an open circuit, again, because we're assuming steady state. Under steady state DC conditions, a capacitor does not have a current through it because the rate of change of voltage is 0, it's steady. And if it has no current through it, it looks like an open circuit. In that initial position, or in that initial state, the switch is in the closed position. So if we go back real quick, the switch is initially in the closed position, therefore the 2K ohm and the 8-volt source are part of the circuit. Okay, and that open circuit voltage is what we'll call VC of 0. So it's the initial capacitor voltage. Alright, so that's what we're going to solve for, and we just use any circuit analysis method that we want. Kind of zoom out a little bit and I'll write a little smaller. So pick whatever analysis method we want. I'm going to say let's use nodal analysis. So to do that I have to set a reference node. And I'm going to call this node over here, maybe I'll use a different color. Call this node V1 and this node V2. Alright, and you may notice by inspection that VC of 0 is V1. So that's the same as that node voltage V1 with respect to ground, which is 0. So we're going to look for V1 specifically. So let's go ahead and write our KCL equations at each node, which is what we do next for nodal analysis. So at node 1, the equations look like this. V1 minus the 12 volt across the 1 k ohm resistor, that'll be the current leaving that node, plus the current leaving through the open circuit. So we just did this one on into the 12 volt source. The current leaving into the open circuit is 0. Because that's the definition of an open circuit, no current. And then the current leaving through the 2 k ohm resistor will be V1 minus V2 over 2 k ohms. And that's equal to 0. Now, KCL at node 2. First current will be V2 minus V1 over 2 k ohm. That's this current from V2 towards V1. Then the current out into the 8 volt source will be V2 minus 8 over 2 k ohm. And finally, the current out to the right through that last 2 k ohm will simply be V2 over 2 k ohm. Alright, and so we'll do some simple manipulations here. For example, KCL equation at 1, I'm going to multiply by 2k. And I'll do the same for the second KCL equation. And what do we get? We get 2v1 minus 24 plus v1 minus v2 equals 0. If I combine like terms, that gives me 3v1 minus v2 equal to 24. Second equation, multiply by 2k, you get v2 minus v1 plus v2 minus 8 plus v2 equals 0. Again, combining like terms, and we get negative v1 plus 3v2 is equal to 8. So now what I'm going to do is I'm going to take that first equation. I'm going to try to get rid of the v2 terms because I want to solve for v1. So first equation, I'm going to say multiply by 3. And when you do that, you get 9v1 minus 3v2 is equal to, what is that, 72. And then the second equation looks like this. Negative v1 plus 3v2 equals 8. Add the two equations, because we could do this to solve for system of equations. Process of elimination, so 9v1 minus v1 gives you 8v1. Negative 3v2 plus 3v2 is 0. And that's equal to 80. So v1 is equal to 10 volts. And we said VC of 0 is equal to V1 by inspection. So VC of 0 is equal to 10 volts. Okay, that's the first part. Alright, so that's step 1. Step 2, we're going to analyze the same circuit but in the final state. So final state means the switch has gone to the second position or the final position. and it's been there for a long time. So as time approaches infinity, therefore we assume steady state conditions again, and that means you have your 12 volt source, you have the 1K resistor, capacitor again looks like an open circuit. You no longer have that 8 volt source because the switch has now opened, but what you have left is the 2K ohm. Again, there's an open circuit between what was left, which was the 2K and the 8 volt, so not part of the circuit, and then you have a 2K ohm over here. And what we care about is the final capacitor voltage. You may ask yourself, hey, we're really looking for the voltage across that 2K ohm resistor on the very right. But in fact, the way we find that is we first find the capacitor voltage, and once you have that voltage, then you use circuit analysis to find any other voltage, essentially. Alright, so this step-by-step method does not work to find the voltage across a resistor or the current through a resistor, only for the capacitor voltage or inductor current. Okay, so I could use kind of simple voltage division to find what my capacitor voltage would be here, right? Because the 1K, the 2K, and the 2K are in series. So VC of infinity would be equal to the voltage between this point and this point. Therefore, according to voltage division, I'm going to multiply the source voltage, 12 volts, times, in the numerator I'll put the resistors that I want to find the voltage across, which are the 2K ohm in series with the 2K ohm. In the denominator, you add all the resistances. So that's 1K ohm plus 2K ohm plus 2K ohm. When you do that, you end up with 9.6 volts. All right, so initial voltage of VC of 0 is 10 volts. Final voltage is 9.6 volts. So very small transition from an amplitude perspective. Okay, so then step 3 is to find the Thevenin resistance of that circuit. And when we're finding the Thevenin resistance, we're looking at the circuit in the final state. We want to see what resistance the capacitor will discharge or charge, discharge into or charge through. So to do this, we do, again, the analysis of Thevenin resistance using what we learned about Thevenin's theorem. So we replace the 12 volt source with a short. We still have that 1K ohm resistor. We're going to look for the equivalent resistance at the terminals where the capacitor is. We have our 2K ohm. Again, we don't consider, so we're looking at it for time greater than 0. So the circuit or the switch is open at this point. So we don't consider that 8 volt and 2K ohm. And now we have another resistor here. So that's a 2K ohm, 2K ohm, and a 1K ohm. And you're looking for R equivalent, or R in, or R Thevenin, all the same, at that point. So R equivalent, which is the same as R Thevenin, is actually equal to the 1K on this side in parallel with the 2K and the 2K, which are in series. Okay, so that's 1K in parallel with 2K plus 2K. All right, and if you do the math, you should end up with 0.8 kiloohms. Okay, so now we know the Thevenin resistance. With that, we can find the time constant. And again, that time constant will be for time greater than 0, so after the transition. And for an RC circuit, the time constant is the Thevenin resistance times the capacitor value. In this case, it'll be 0.8 kilo ohms, and the value of the capacitance is 2 millifarads given in the initial circuit. All right, and then you do that, and ohms times farads will give you seconds. So make sure you take that into account with your units. But you'll end up with 1.6 seconds. And finally, steps 5 and 6 are pretty straightforward because you're really just plugging into, well, at least for 5, you're plugging into the general equation. So Vc of t is equal to the final voltage, 9.6, plus, in parentheses, the initial voltage minus the final voltage. All that times e to the negative t over tau, which is 1.6. All right, and that's going to be in volts for time greater than or equal to 0. Okay, so then we kind of evaluate that or simplify it, and you should end up with 9.6 plus 0.4 e to the negative 0.625 t. So if you say 1 divided by 1.6, you get 0.625 t, and that's in volts for time greater than or equal to 0. Okay, so now we know capacitor voltage for that initial circuit. But that's not what we were looking for, actually. We were looking for the output voltage across that 2K ohm at the very right. So let me go back to that initial circuit. Okay. The 2K ohm at the very right. After the switch opens, the 8-volt source is no longer in the circuit. Therefore, after the switch opens, the capacitor voltage is actually just the voltage across both of those 2K ohm resistors that are in series. They're in series again because the switch is open and the 8-volt, that branch that has the 8-volt source, it's no longer part of the circuit. So make sure you can visualize the fact that capacitor voltage is the voltage across the two kilo ohm resistors in series. And once you know that, you're looking for the voltage across this guy, one of the 2 kilo ohm resistors. So we will go ahead and do voltage division. Okay, so V out of t is equal to Vc of t times one of the 2 kilo ohm resistors, the one that you're looking for the voltage across, divided by the sum of both of the series resistances. So 2 divided by 4 is just half. So you're multiplying 0.5 by the Vc of t function. And when you do that, essentially you're doing this. You end up with 4.8 plus 0.2 e to the negative 0.625 t. That's in volts for time greater than 0. Alright, so hopefully this example made sense. Make sure that you feel comfortable with this type of example. So this, a circuit of this amount of complexity is what you would be expecting to do on a quiz and also on the homeworks. And again, feel free to email me if you have any questions about this particular example, and hopefully you also check out the other two. Thank you.